Okay, let us look at these questions. Yeah, equilibrium of rigid body. A hanging flower basket having a weight W2, okay, 23 Newton, is hung out over the edge of a balcony railing on a uniform horizontal beam AB, okay, of length 110 cm that rests on the balcony railing. So what I can say is this is the balcony railing. Yeah. The basket is counterbalanced by a body of weight W1 as shown in the figure. If the mass of beam is 3 kg, calculate the weight W1 needed and also the force exerted on the beam at point O. Good. Now, to do this question, okay, remember this is a rigid body, not a particle. This is a rigid body. So it's not equilibrium of particle. Not equilibrium of particle. Yeah, remember that. So for rigid body, you will need to fulfill two conditions. Sorry, hold on a second. Okay. So for rigid body, you will need to fulfill two conditions. We need to fulfill total F equal to 0 and also total torque equal to 0. And also for rigid body, we draw it as a rigid body. We draw the whole body of the object. We don't draw just a point mass or just a particle. Okay, when we draw the free body diagram, we draw the whole body. We draw the whole body. We don't draw just one particle. Okay, because this is a rigid body. Because we are thinking not just force in translational motion, we also think the force will make the whole object rotate. Yeah, when the forces is exerted at different point of the body, it will make the object rotate either clockwise or anti-clockwise. Okay. So we need to draw the whole body. Yeah. So first of all, to do this question, we need to draw the free body diagram. Yeah, draw the free body diagram. But before we draw the free body diagram, let us identify what is our target object here. So if you look at here, all our focus is just on what? On the beam AB, on the horizontal beam AB. This is actually our focus. Not on the weight 1, not on the weight 2, the flower basket. No, our focus is actually just this. Our focus is actually just the beam. You understand? Just the beam. Not the flower basket, not the weight. Our focus is focusing on the equilibrium of this beam. Understand or not? Okay, so we just draw the forces on the beam. We don't draw the force on the basket. We don't draw the forces on the weight 1. Okay, remember. So our focus is just the beam. Yeah, because we are talking about the equilibrium of the beam. We are talking about the equilibrium of the beam AB. Okay, we don't talk the equilibrium of the flower basket. We don't talk about equilibrium of the weight 1. No, it's all about the beam only. So only draw the force on the beam. Yeah, our target is the beam. This is our target. This is our target object. Okay. So now, first of all, identify what are the forces acting on the beam. So we just roughly draw. So first of all, he said that this the flower basket has a weight W2. Okay. So we can say for this beam, it has the forces going downward here. Okay, yes, forces going downward here, which is W2. The flower basket pulling the beam at this point downward. Okay, and also this body here has weight 1, so it's pulling this weight 1, also pulling the beam downward also. Pulling the beam downward also. This is W1. Okay, You must label with W1, W2. Don't just write W. Okay. And then he also said the whole beam has weight, isn't it? He said this beam AB of length 110 cm, the mass of the beam, you see, here also he said the mass of the beam is 3 kg. So that means the beam itself also has mass, not just the W1 and W2. So the beam itself also has mass. So normally for the beam, this is a uniform beam. You see that? This is a uniform beam. So if the beam is uniform, that means the center of mass is at the center. Because why is it the center of mass is at the center of the beam? Because this beam is uniform. It's uniform. So we don't. Uniform means not one part of it is bigger than the other part. This part, we don't say, oh, this part has bigger mass, this part has a smaller mass. No, it's uniform. If uniform, then the center of mass must be at the center. If non-uniform like this, remember, imagine if a non-uniform object like this. So where do you think is the center of mass? The center of mass is at somewhere over here. It's not at the center. You understand or not? This is if non-uniform. If this is a non-uniform object, non-uniform beam or non-uniform object, then the center of mass is not at the center, is over here. This here got the weight of the beam. Understand or not? But for uniform beam, then the mass of the center of mass must be at the center. So we draw at the center. This is the weight of the beam. Okay, at the center. This one is off center, not at the center. It's off center. Okay, put this somewhere else. Group this and put this somewhere else. Right. Okay, let us continue. So for this is a uniform beam, so the weight of the beam must be at the center. Okay, we can say this is at the center. And he also say the whole beam is 110 cm. 110 cm. So since the weight of the beam is at the center, that means it divide the whole length. The whole length is 110 cm. So it divide the whole length by half. So we can say what? We can say from here to here is how long? From here to here, so 110 divided by 2, you get 55 cm. 55 cm here, 55 cm here also. Understand? Because the weight of the beam is at the center. Now, okay, this thing is equilibrium. This whole beam is equilibrium because it's a counterbalance. So it's equilibrium. And then he say this beam is resting on the what we call the balcony railing. This is the balcony. Okay, so it's resting on top of it. On top of the balcony. So we can say here got a supporting normal force going upward. Supporting normal force going upward. There's a normal force here. Understand or not? Normal force at point O. So this is question B. He asked for the force exerted on the beam at point O. So which is the question actually asked for normal force. For question A, he asked question B asked for normal force, which is the supporting force by the balcony to the beam. Okay. Question A asked for weight 1. Question B asked for the normal force. Okay, force exerted on the beam at point O, which is the normal force. Okay, so what other forces acting on the beam? Any more? The weight of the beam, W1, W2, the normal force. I think that's it. No more other force. So we have identified all the forces on the beam. Remember, our target is the beam only. It's not on the W1, not on the flower basket. Okay, now let's draw our real free body diagram here. Let's draw our real free body diagram over here. Okay, so what you have to draw is, don't draw just a point mass because this is a rigid body. Now it's a rigid body, free body diagram of a rigid body. So it's a body, not just a point mass. Understand? It's a whole body. So what you have to do is you draw the beam. Our focus is only the beam, equilibrium of the beam. Okay, so let us draw it out. Let us draw it out. So this is the beam. Yes. Okay, and then what do you do? Okay, write the point there. So we have here is a point A, and here is a point B, and here is a point O. Okay, actually here there is a supporting. Yeah, we can say this is like a fulcrum. The balcony is like a fulcrum supporting the beam. Okay, so draw all the forces on the beam. So we have what? Just now we have W2. W2 we have and then the W1 pulling it down over here. We have the weight of the beam at the center. Okay, this is the weight of the beam. And don't forget the normal force. Okay, this is the point O. This is the normal force. Okay, let me draw it carefully. Yeah. Yes, this is the normal force supporting the beam. Okay. So that's it. I think we need to maybe you can write down the distance later on. Yeah. So this is our free body diagram. Okay. So don't draw all other things. Yeah. Just draw the beam. So we are talking about the equilibrium of the beam. Yeah. Let me write down. Okay. I already written down here. All right. So we are actually just talking about the equilibrium of the beam. It's just the beam, our focus. Okay. Now write down the value. Yeah, over here. What we have is W2, the 23 Newton. Okay, write down. It is useful. Yeah, write it down over here. This is 23 Newton. And what else? The W1. How big is? We don't know. We need to find this one. Yeah, we don't know this one. What is the beam? The beam weight. The mass of the beam is 3 kg. So we can say this mg. So 3 times gravity. This is not gram. This is not gram. This is gravity. Yeah, it's 3 kg multiplied gravity. Then we get the weight of the beam. Then the normal force we also don't know. That's we want to find. Yeah. So how to find the weight? Okay, how to find the weight? Okay, so from here we can see there are okay. So for equilibrium of rigid body, yeah, the beam is a rigid body. The beam is the rigid body. So talking about equilibrium of rigid body, okay, it need to fulfill two conditions. Which I stated. Total F equal to 0, total torque equal to 0. So maybe you can write it down here. Okay, copy this over here. Okay, just for reference. Yeah. Okay. So equilibrium of rigid body. So for rigid body, it needs to fulfill two conditions. Total F equal to 0. F also we have X and Y. And this is the direction. We put positive or negative. And torque, okay. Total torque equal to 0. And this is the direction. Clockwise, negative, anti-clockwise, positive. Okay. Anti-clockwise or counterclockwise. Okay. So for this case, to find the weight one and the normal force, which one can we use? Does it have any x component? Do you see any x component force here? No x component. No, yeah. It just have y component. It just have y component. So we can use the y component. Another thing is we can use the total torque equal to 0. So we will have two formula. We have one formula for total Fy equal to 0 and total torque equal to 0. Okay? So let us do it here. We can make tables, but for this case, this is a simple example. So the table is not necessary. Yeah, the table is not necessary. So okay, we can use, because no x component, only y component. So we can use the first formula. Because this is equilibrium. Yeah, equilibrium. So total Fy. Okay, this is the y component. Total Fy will be 0. Total Fy will be 0. Okay. So now, let us start. Yeah. So, which are the forces going upward? Normal force. So normal force is positive. Yeah, normal force going up positive. So forces going up, we just look at the y component. So we just use this one. All the forces going up is positive. Forces going down will be negative. Okay? Forces going up positive, going down negative. So normal force going up, so it's positive. So we put that normal force as positive. And then for W2, W1, and the beam weight, all of them are negative because all of them going downward. So write negative, negative, negative. Okay, so I want to write it. First we have the W2, and then we have the okay, then we have the W beam. Then we have the W1 equal to 0. So solve already for y component. Okay, we got one equation already. So this is the normal force minus W2 is 23 Newton. Okay, and then minus the beam is 3 times gravity, and the W1. Okay, so we cannot solve this equation because we have two unknown. We have the normal, and we also have the weight one. Weight one, we don't know. So this one have two unknown. That means I need another equations. Then only we must have at least two equations because we have two unknowns. That means we must have two equations to do simultaneous equation. Then only we can solve to find the normal force and the weight. Okay, so that is we need to use another formula, which is total torque equal to 0 for equilibrium of rigid body. See for free body diagram, for rigid body, we don't draw a point mass, we draw a body, yeah, not just a point mass. Remember that. Okay, next is we use the total torque equal to 0. Okay, for total torque equal to 0, you need to set a point as axis of rotation, because you are talking about rotational motion here. So rotational motion, when the object rotates, it must rotate around an axis of rotation. So there must be got axis of rotation, then only the object rotate, isn't it? It must rotate around the axis of rotation. You cannot have without axis of rotation. So this one, where is the axis of rotation? So likely we choose, remember what I said before? Axis of rotation, you can choose any point. You want to choose point A as this axis of rotation. You want to put axis of rotation over here, also can. You want to put axis of rotation here, also can. You want to put here, also can. Put here, also can. So anywhere also you can put axis of rotation. But we must choose the position wisely. Normally we choose the position with unknown force. So we can neglect the torque by that point. Understand? So all right, let me continue. So we choose the axis of rotation over the fulcrum here. Then because this one got unknown force, if the axis of rotation we put over here, okay, put over here, That means this normal force has zero torque. Because why? Because the distance is zero. The distance for this normal force is zero. So the torque, which is Fr sine theta, okay, so will be equal to zero also. Understand or not? Because this normal force acting directly on the axis of rotation, so you have zero distance. We have zero torque. Okay, so I choose axis of rotation here easier, so that I in the equation the torque by normal force becomes zero. So actually we can eliminate one variable already. So the formula will just have the W1 only. Don't understand? Let's see. Yeah, let's see how I solve it. Okay, if you don't understand now, never mind. You can understand later. I will show you. Okay. All right. Now let us do it. Yeah. So first of all, look at W2. W2. If the axis of rotation is over here, how do W2 rotate? How do W2 rotate the object? If the axis is over fulcrum here, this W2 will make this object rotate. Rotate what? You not sure? Draw it out. You draw from the axis of rotation and then follow the force. See? From the axis of rotation, then follow the force. So you can see this is what direction? Anti-clockwise. So truly, if the object pull over here, this point B will go up and point A will go down. So the object will turn anti-clockwise, isn't it? Will turn anti-clockwise. So this is the torque. This is the torque. We can put as torque 2. Okay, we put it as a positive torque or a negative torque. Remember this one. Torque that are anti-clockwise is positive. Clockwise is negative. This positive negative is just direction only. It's just like direction. Should highlight it. It's just like direction. It's the same direction like last time in the linear motion. Going to the right is positive, going to the left is negative. But for rotational motion, we don't say rotate to the right, rotate to the left. We don't have things like that. The rotation only got two directions: rotate clockwise or rotate anti-clockwise. So rotate clockwise we put as negative torque. Rotate anti-clockwise we put as positive torque. Understand? So this torque 2 by weight 2 will make the object rotate what? Anti-clockwise. Yeah, you can imagine like this. This is the axis of rotation. Okay, initially it's like that. Okay, when you pull over here, W2, I become like that later on, isn't it? And then become like that later on. You see that? So this direction is what? This direction is what? Anti-clockwise, isn't it? Anti-clockwise. Anti-clockwise we have what? We have negative. This torque 2 become positive torque. It's a positive torque because it's a anti-clockwise. So we can put this one as positive torque. This is a positive torque because anti-clockwise. Okay, this is a useful diagram. Just put it somewhere else first. Okay, for reference. Maybe I put it over here. Okay. So this is W2. W2 make the object rotate anti-clockwise. Okay. Now how about and the normal force? Normal force, this one has zero distance, because this normal force acted directly on the axis of rotation. So the R is 0. When R is 0, the torque is 0. So this one has zero torque. And then how about the beam? The beam will make the object rotate clockwise. So you just draw. You draw first from the axis of rotation, then follow the again from the axis of rotation, then follow the force. From axis of rotation, then follow the force. So this is torque by the beam. Torque by the beam. Put torque B. Okay, and this is a positive or negative torque. That means this you see is a clockwise torque. If you don't understand, let me draw it out. Yeah, let me draw it out. This is the beam. This is the axis of rotation. Axis. I pull it over here. This is the W beam. Okay. So after some time, this object will rotate. Yeah, rotate here. Will like become like this. See or not? Will become like this, and then become like this. So it make the object rotate what? Rotate clockwise. Do you see that? Do you see that? So this is torque by the beam is clockwise. Is clockwise, so it is a negative torque. Okay. For clockwise, torque is negative. Okay, it rotate this way. Yeah, it make the, because axis of rotation is over here. See that? Axis of rotation. This one, axis of rotation here, and this is the force. Yeah. So you pull over here, it make the rotate anti-clockwise. Okay, this is something useful. I should put it in somewhere else. Okay, it's so useful. Okay, I'm so tired. You understand? I'm tired actually after talking so much. Okay, I think you will miss me after this. Okay, so we have a clockwise torque. Yeah, this is a clockwise torque. So this torque B is a clockwise torque. You just look at the shape. This is a clockwise direction, isn't it? Clockwise is negative torque. So it's a negative torque. Negative torque. Okay. So how about the W1? How about the W1? Same thing like the W beam. Also rotate anti-clockwise. Okay, you look at where is the axis. Axis over here. So you start from the axis and then follow the force. Force is going downward. From the axis downward. So this is the clockwise. You see that? It's a clockwise. So this torque number 1 is a clockwise. The clockwise. So it is a negative torque. When clockwise is a negative torque. Negative torque, yeah? Clockwise is a negative torque. So it's this one is like the beam lah. Torque 1 is like the torque beam. Yeah? It's like torque beam. If you apply the force over here, this is the weight 1 just now. Weight 1 also. So it will also make the object rotate clockwise. So I can say over here, the torque 1 also negative, okay, because it make rotate clockwise. Okay, so you have 2 negative torque, you have 1 positive torque. Yeah, you must have positive. We must have positive and negative. You cannot have both positive or both negative, because your total torque equal to 0. You must count. That's why I can say it counterbalance. You understand not? That's why he say the basket is actually the weight to. Understand not? The basket is the weight to. It is counterbalance. Counterbalanced by the weight 1. Yeah. This is the basket. The weight 2 is the basket. Make the object rotate anti-clockwise. But the basket is counterbalanced by the weight 1. Because weight 1 is opposite direction. The basket rotate anti-clockwise, but the weight 1 rotate clockwise. So it's counterbalanced. The basket also counterbalanced by the weight of the beam. Not just counterbalanced by weight 1. This weight 2 also counterbalanced by the weight of the beam. Okay? So then only become the total torque equal to 0. Total torque equal to 0 because their torque are counterbalance each other. Okay, so now let us build into equations. Okay, I have explained. I just explained about the direction and also the positive and negative sign related to the direction of rotation. That's it. Okay, you can refer to this one. Okay, so now look at this one. So we have start with torque 2. Torque 2 is a positive torque. Positive torque because it's a okay, just now this one is not positive, no move. Okay, this is a positive torque because it's anti-clockwise, but the rest, torque beam and the torque 1, they are negative torque because they are clockwise torque. Negative. Okay, so we have negative torque beam, we have negative torque 1. Okay, equal to 0. Okay, now once we have the direction, now we apply the formula. Torque is equal to Fr sin theta. Okay, Fr sin theta, where here the theta is actually angle between what? F and R. F and R. Okay, so now look at torque 2. Log torque 2. What is the force? What is the force? What is a force? Weight 2, isn't it? So we write as weight 2. We write as weight 2 multiplied by how far is the distance? Okay, R is distance from the force to the axis of rotation. How far is it? How far is it? Look at here. I already write the distance here. I don't want to put all information in one diagram because it will make the diagram become messy. Yeah. So I borrow some information from here because these two diagrams actually is the same. Okay. So look at so I need to find what distance. I need to find this distance. This is the R. Yeah, this is the R. The R for the distance. The R for torque 2. The distance from W2 to axis of rotation. This is the R. So how far is this? How far is this? Yeah, AO. AO is 35 cm. 35 cm. So you can put as this one is centimeter. You need to change to SI unit also. Yeah, this is a centimeter. Change to meter. Okay. So divide by 100. Divide by 100 is 0.35 meter. 0.35 meter. So the distance is this is 0.35 meter. Okay. Understand? 0.35 meter. So okay, let's write it down. So this is distance 0.35. Okay, and then sine theta. Sine theta. Sine what angle? What angle? What angle is the angle between the force and the R? Very simple. It's 90 degree. It's 90 degree. Remember, the theta is between the force and the R, and they are perpendicular to each other. Perpendicular, so angle is 90 degree. So this is sine 90. Okay, sine 90. Okay, we got it ready. Yeah, just convert all this into green. Okay, so that's the first torque for torque 2. Okay, so now let's continue with okay, the normal force has no torque. I just want to rub this off. Yeah, not needed anymore. Okay, so for normal force has no torque. Now how about the beam? The beam has torque beam. Yeah. Okay, so first of all, what's the let's write it down. Negative. So what's the force? The weight of the beam. The weight of the beam, just put WB. And then we have the, what is the distance? How far is the distance? So the distance is, what is the distance? From the weight of the beam to the axis of rotation. So this is the distance. This is the R. Understand? So what is the R over here? What is the R over here? Okay? How far is from the beam to this point? Okay, how far? Okay, how to calculate this R? Very simple. Because from A to the center is 55 cm, the half of the length. And then from A to O is 35 cm. So how far is this point? 55 minus 35, which is 20 cm. So the R here is 20 cm. Understand that? O here is okay. Rub this off first. From here to here is from here to here is 20 cm. Because it's 55 minus 35. So we have 55 minus 35, we have 20. So from here to here is 20. So that's 20 for the beam to the fulcrum, 20 cm. So 20 cm is 0.2 meter. You need to change to SI unit. It is 0.2 meter, 0.2 meter. Again, also 90 degree, isn't it? The angle. Angle is 90 degree. Angle is 90 degree. Yeah. The angle is 90 degree. Okay, so it's sine 90 again. Oh, sorry. Is sine 90. Sine 90. Okay. And then what's the rest? And then finish already. Top B. How about top 1? Top 1. What is W1? We don't know. Put as W1. And then how far is W1 to the OB? How far is it? What is the distance? This is the distance we want to find. Yeah, from B to O. This is the R. How far is the R? How far is the R? From B to O. How far? Given already 75 cm. See or not? From O to B is 75 cm. That's our 75 cm. Okay. Let's rub that off. So it's 75 cm, which is divided by 100 is 0.75. Okay. 0.75 meter. Okay. What's the angle again? Angle is also 90 degree between the force and the distance. So it's also sine 90. Equal to 0. We have done it. We have done it. Okay. All this sine 90 actually equal to 1, isn't it? Sine 90 equal to 1. And then we put in the value for what? For W2 and W beam. Put in the value. Okay. So this is 23 times 0.35. And then minus what is the W? This is 3. W beam is 3 times gravity, and then multiply by 0.2. Okay, that's it. And minus W1 times 0.75 equal to 0. Okay. Here I can find my W1, isn't it? I can find my W1. Now let's calculate W1. Okay, so I got the answer already, which is 2.89 Newton. That's the weight one. We got the answer already. It is 2.89 Newton. Okay, is it correct? Is it correct? Yes, it's correct. W1 is 2.89 Newton. Is correct. 2.89 is correct. So is it? Equilibrium. Total torque equal to 0. We can solve it. Find the W1. Now, how about finding the... We need to find what? The normal force now. We need to find the normal force on beam. This normal force. How to find this normal force? Okay. So we have two equations. We already have W1. Now we just substitute into here. We can find the normal force. Okay? So simple. Yeah? That's why we need two equations. We can do simultaneous. So the normal force. Okay, this is for question A. So this is for question B. Okay? Question A done. Question B on the way. Yeah. Okay, minus 23. All right, let's continue. Minus 3 times gravity minus 2.89. 2.89 equal to 0. So what's my normal force? Let's calculate. I got the answer already. Okay, which is the normal force is equal to 55.32 Newton. Is that answer correct? Okay, is the answer correct? Yes, it's correct. The normal force is 55.32 Newton. It's correct. Yeah, 55.32. 55.32. That's correct. Okay, so that's the normal force I got from the answer. Okay, that's the supporting force. We can rub that off. All of that can rub off. Only the torque is 0. Wait, let me. Okay, so never mind, just leave it there. So we can say this is this normal force is 55.32 Newton. That's the value of this normal force. Value of this normal force. It has the normal force 55.32 Newton, but for torque is this 0. Yeah, if the axis of rotation is over here, the torque is 0, but the normal force is 55.32 Newton. For the weight is 2.89 Newton. Okay, and this whole object is equilibrium, right? This whole beam is in equilibrium. This whole beam is in equilibrium. Okay, we are focusing on the beam only. We don't focus on the other object. Only the beam is our focus. Only the beam is equilibrium. Okay, so that's all for this question. Thank you.